They have like all these violins, cellos, and everything.
That was the most
these like chromatic
random guess.
Yeah. Oh, it's so,
That's the one he was talking about.
Creepy. It's so creepy. Like it makes you think of like screaming.
And it was about the Hiroshima.
It was like a tribute to the Hiroshima bomb.
Tribute.
Not to the bomb itself, but to the bombing. You know, like
in memoriam,
yeah. It's pretty twisted. It was pretty crazy.
I would say that sounds twisted off the bat if you're saying tribute to the world. It's like, whoa! All right. So no specific questions from 4.7? Okay, so we're going to do a couple more examples from 4.7 just to get the feel for how these things work. And one of my of course, I'm the only one here that would probably say this, but one of my favorite type of problems here is, for example, number 20 on page 332. It's not too much on there, so I can just tell you. Number 20 says, find the point on the curve y equals square root of x that is closest to the point 3, 0. So, just to get a feel for what's going on here, we have square root of x, 1, 2, 3, 4. So this is going to be 2, 1. Here's 1, 1. Yay, it actually works here. And so I want to get the point that's closest to this point. And distance is always measured in terms of sort of like being perpendicular there. So the point that minimizes this distance, so I can kind of approximate and say it's going to be this point here. So I love this question because it's, when you first look at it, you're like, what the hell do I do here? There's no volume here. There's no shit. There's nothing here. But what am I trying to minimize? What idea, and then what's the function that goes along with it? What am I trying to minimize here?
Distance.
Distance. And how do I get the distance between 2 points?
Square root of
So the distance formula,
square root x minus x1 squared.
yeah, x1 minus x2 squared plus, right? Doing okay? Doesn't really matter which way you put x2, x1 because it's squared. Okay. Now the nice thing is, now you can imagine, if you start to think ahead to what you're going to have to do with this, if you want to minimize this function, you're going to have to take the, and my God, I don't want to do that with a square root. So the beautiful thing about the square root function, if you find the extrema of the input, that's automatically the extrema of the root itself. Does that make sense?
Yeah.
So thank God I can actually just look at the function d squared. Coolness. So what are my points that I'm plugging in here? What am I going to put in here?
X minus 3.
Yeah, so it'll be like 3 minus, or x minus 3. I like it. Cool. X minus 3 squared plus
Y minus 0.
y minus 0 squared. And that's my d squared function. How are we doing so far? So basically every problem in there, almost everyone, I got to cover my ass here just in case. Almost every problem in there that says find the point on this curve that's closest to here or does something, you can set up this distance formula and just attack it. And then what's still wrong here? This is where it kind of comes back into what we're used to. We've developed a function that matches what they're asking me to minimize. They want me to minimize the distance. There's the function I want to use for the distance. I can minimize it. What's wrong currently with the way it is? How many variables are there in there?
3.
Well, there's 2. The d the d doesn't matter really by itself. I'm just going to take the derivative of this side is all I'm really curious about. Don't worry about 2d d prime crap, by the way. This is a function. And I'm just going to take its derivative. So I'm going to derive this side. The problem is that y there, right? So what is y?
Square root of
Yeah,
x.
so use what they tell you in what they ask you. So they asked me about the distance. I write that formula down. I use what they told me in it. So it's really the same format as the other ones. Just doesn't feel like it at first. So then I get d squared equals x minus 3 squared plus square root of x squared is x. It's crazy. All right. Then you take that guy's derivative. Again, don't overthink this.
How did you get to 1 minus 0 squared is equal to x there?
Oh, y equals root x.
Oh, okay.
And then root x squared.
Gotcha.
Good.
Okay.
So how do you take that guy's derivative? All right, good. I love it. So I love this look in your faces. The only thing that's different about section 4.7 is how you get to the function. Once you get to the function, you take its derivative like you always have, right? So 2x minus 3 plus 1. So you could FOIL this out, add this in. Why would you? One derivative and there's, the power's gone. Who cares, right? So notice things like that. If you did FOIL it out, it'd still work. Who cares? Right? You still get there. So I get
2x minus 6 is 1. 2x minus 1.
and then what do I want to do with this?
Solve for
That's
x.
for rid of it.
Solve for x.
Equal to 0.
You're missing one thing. Set it equal to 0. If I'm trying to find the minimum distance, I take its derivative and find where it turns, and this is going to be where the slope is 0, right?
So is that the minimum distance though if the slope is 0?
To find the minimum blank, I set the derivative of blank to 0.
Okay, the first derivative of blank.
Exactly.
Okay.
Exactly. Right. Sounds like a good band name. We are the first derivative of blank. And so now I just take this, set equal to 0, and get x equal to 5 halves. And looking at my approximation for this, doesn't that look like about 2.5? Admitting that my picture is ugly. I didn't know the answer ahead of time. Even with such an ugly answer, I still got close to it, right? So at 5 halves, this point would be the closest to this point. And of course, to finish the question, what is the point then? Find the point that is closest. So it would be the point 5 halves.
Substitute.
Over root 5 over 2.
Square root of 5 over 2, yeah. Whatever the hell that is. So, sweet.
Wait, what?
To complete the point, you have to plug it back into the function, right? I like it. And you already defined for yourself what the point is. That's y, and y is root x.
So the question was find the point on y squared farthest to this point.
Oh yeah, there's no answer. Because the farthest point is, the limit is this goes to infinity. Right? Because you get further and further as you let this go bigger and bigger. So you normally won't be maximizing the distance unless you have some function that's contained, you know. Does that make sense? Like an ellipse and a...
The same procedure will be carried.
Yeah, so you could do that if I had an ellipse and, you know, a point, and I want to know what's the furthest that this ellipse gets from this point. But if you have a function that's not contained, then the answer, you don't need any calculus. Just limit as it goes to infinity. Next problem, right? But it has to be some kind of contained function to make the maximum make sense. Cool, is that cool? No, okay. All right. Let's see. So there's several that are like that. And then there's several that are like this. Like number... Oh, which one was homework? I can't remember.
This is on 3.7.
4.7, yeah.
4.7.
What was the homework for that? Yes.
So what do you do for something like for the ellipse if it is a closed function?
Let's see if we can make a problem up. This is always scary. So if I had the ellipse, somebody help me out. Make up an ellipse for me. It's not too crazy.
X squared.
X squared. Yeah.
Plus y squared over 16.
1.
I like it. So there's my ellipse. I know it's in a circle because these aren't equal. I like it. And let's see what's going to make sense. So this is going to be my, I got this kind of turned around, don't I? Because what should be longer?
The y.
Of course, I don't feel bad because I drew the ellipse before I knew the function was. So it'll be more like that, where this is going to be
4.
4, negative 4,
3.
negative 3 is 3. So then maybe this point looks to be like 4, 6. So I want to know what's the point on the ellipse that's furthest from that?
And then that's any point on the ellipse per se that we can that's possible. Right?
Yeah, yeah.
Okay.
So, I mean, you can kind of tell it's going to be sort of like here somewhere, right?
Yeah.
Just to get a rough guess. But, of course, calculus gets me the exact answer. And this is the point, again, this is the point 4, 6. So, how do you find, first thing you got to do, you know you're going to be on the lower part of this ellipse, right?
Yes.
So you can solve this for y and pick the negative part, and then it becomes a lot like that problem. Are you with me? It becomes very much like that problem, yeah.
How did we find 4 and 6?
Say it one more time.
How did we find 4 and 6?
I just gave it to you. It's got to be part of the problem.
Materialized out of thin air.
Exactly. It did, totally. The same way that 3-0 did on that problem. They have to give it to you. Yeah.
Great, thank you.
Does that make sense? I mean, they have to give it to you.
So how come you're choosing the most negative point?
I'm just saying, what's the furthest from this point?
Oh,
What point on
furthest.
here? That, not that one. That's, this is further, and somewhere in here starts to get closer to it again. So somewhere in there is going to be the furthest away. You guys want to work that problem out, or do you want to? What's going on here? Yeah, okay. So if you solve this for y, what's going to happen?
Subtract x squared. Wait.
Yeah, subtract x squared over 9.
And then divide and multiply by 16. I like it, and it's going to be the negative one, right? So, and I need a square root in there somewhere. Okay, there you go. So subtract, multiply, take the square root, pick the negative root. So far, so good?
Yeah.
So then y equals negative. You can even do this for yourself. See if you guys are cool with this. 16 comes out and becomes 4. Over 9 comes out and becomes 3. Since that was a 1, I have to put a 3. We saw that kind of thing the other day. Not a 3, I have to put a what?
9.
9, thank you. Okay. So if you divide a 9 out, right? So you're not dividing a 9, you're taking a 9 out. So you're dividing a 1/9. 1 divided by 1/9 is 9. So if you put the 9 back in on the bottom, wouldn't 9 over 9 equal 1? That's the kind of thing that shouldn't be too big of a reach for you to be able to do, to make sense of.
If you're dividing by 1/9 though, negative 4 divided by 1/9, shouldn't that be?
No. I'm taking a 1/9 out.
Okay,
So everything
just from
inside
a little-
is being divided by 1/9.
Okay,
And the 1/9 comes outside. So what did I do here? I took a 16 out. So everything inside is being divided by 16, but I put the square root of 16 just out here. Right? It's the same way either way. This just makes it better to look at. Yeah.
So, the only thing I'm not following is how come the 9 minus x squared is still left on the inside?
So the only thing I took out was the 16, was the 4.
Right.
And let me do this for us. Is that cool?
Mm-hmm.
So the over 9 can come out as over 3. So then what do I have left inside? 9 minus x squared. So if you make LCD, it actually makes it easier to look at. But hopefully. So now the over 9 can come out of both, and you're left with what's on top. Now the work is going to be exactly like the work was there. It's just a little worse. Because my function's a little bit worse than root x. It's this, right?
If it was closest, we would choose the positive.
Say again?
If it was closest to the ellipse, we would choose the
Exactly.
positive.
So in that case, because this is not an invertible function, you'd actually have to consider that you have to be careful about which side of the function you want to pick. So you're right. If it was closest, we'd have to draw it out and say, oh, I want the positive part. I like it. How we go so far? Okay. So this is going to be truly disgusting. So, and again, I just made this up out of nowhere. The reason I know it's going to be truly disgusting is because the nice thing about this problem was right here. True? Because then the square applies directly to the y and it kills the root. Here, the square is not going to apply directly to this y because I've got a y value there. Oh, crap. Right, so when I take the difference, I don't know if you guys can see it. So I know that this distance formula is going to be the same as it was before. Good old Pythagorean theorem applied to points. So then I can say, so here's my point x, y. So I got x minus 4. Is that cool? For the x values. x minus 4 plus y minus 6. Where y is
4/3.
this thing. But the nice thing is you're just taking derivatives, and it's just going to look more disgusting, but you're just taking derivatives, right? So it's still workable.
So, the information you have there on the bottom.
That tells me any y on the bottom part of the ellipse must be related to x this way.
Okay.
So when I take the distance between that point and some point on the bottom part,
Uh-huh.
I can replace y with this, because that's what I know every y on the bottom part is.
Okay.
Then I have one variable. Once I plug this thing in, I have just x to worry about on that side.
And so, is it in the distance formula, or in this case, normally, does it? Do you have it as d squared, or is that just because of the problems?
For the distance formula, you always do that, because if you left the radical, it would have to be, when you do the derivative, that radical is there.
Mm-hmm.
Which now you have a chain rule with the radical, and it just becomes really disgusting. And math says, why do that to yourself? If you just minimize or maximize the inside, you'll minimize or maximize the root of it.
Gotcha. Okay.
Because the square root's all on the positive side anyway. It's nice. Hopefully that makes sense. It's really awesome that math lets us do that. Yeah.
I have a quick question on the part that you circled. How do we get an x?
Say again.
How do we get an x on that part that you circled?
What's y equal to in this problem?
Root x.
And what's root x squared?
Just x.
Cool. Okay. I don't know if I want to keep going. I mean, I think the important thing to get, we could keep going. And it would just be different. The only reason it would be different from that problem is because the function I'm working with is different. But it still was the exact same setup. I used the distance formula. I plug in the point and some arbitrary point, pop, and I've got this expression for the y piece of my arbitrary point. Throw that in there, take derivatives. I'm not saying the derivative is going to be nice. It's not. But derivatives, you can always attack derivatives, always, right? It's the antiderivatives coming later that we can't always attack.
So do we not take the derivative of d squared because we're setting it to 0 anyways?
No, well, we do take the derivative of d squared, and then we immediately set it equal to 0, and that's why I'm not worried about like an implicit differentiation stuff here.
Oh.
Don't even worry. It's just whatever the hell that is prime, I'm going to set it equal to 0 anyway. That's why I don't even worry about that side. Good, you're good. Okay. Is that good enough to keep going? Yes?
Is this something we've seen on tests or like a bonus problem? Because this kind of
Yeah, this would definitely be a bonus problem, but since it came up, I wanted to show you how the thought process was the same. The work involved in that is different because it's a different function, but I'm still just taking derivatives, setting what I got equal to 0, right? I can almost guarantee you that this thing will be gross. In fact, I don't know if we can set it equal to 0 and do it by hand. So I would definitely not give this problem on the test. But at least I want to get it that far and show you the setup and the thought process, the exact same as it was on this problem. The exact same it is on most distance problems. Find a point here that's closest to this. You guys got it with me? You can even say find a point on this curve that's closest to a point on that curve. Right? And then actually it's sort of like comet coming in, the Earth, or, asteroid or whatever, and you got the Earth's motion and the asteroid's motion. What's the closest approach? Oh shit, that sounds like a good problem to figure out. All right.
sounds like a bonus problem.
Yeah, it sounds like a Bruce Willis movie. All right. Okay. Okay, so looking at number... Is number 16 part of the homework in 3 and 4-7? It's a really good time to lie, but I'll trust you.
No, it's not.
Okay, so we'll try. It is?
Int.
Int. Okay. I like that. It is. Int. Alright. You'll love number 16. Number 16, there's problems like it, but number 16 itself involves an extra layer. So you have a lot of problems with like an open box, and you want to use so much material, and what's the biggest volume you can get out of that, right? And then I'm like, what's your life like that you want to actually figure that out? But we're just learning how to use the calculus. So number 16 adds an extra dimension and adds cost in. So there's different costs for the different sides. So I like to do problems like you want to fence it around, but one side you want to use a special kind of fence, so it costs more money, and the other ones cost less money. You want to minimize the cost. You kind of with me? So it's a little bit different. So number 16, rectangular storage container with an open top is to have a volume of 10 cubic meters. 16 on page 3.
This is 4-7
32.
still.
So again?
This is 4-7 still.
4-7 still, yeah. So it's open top. Yay. 10 cubic meter volume. So this is what they tell me. And then they say the length of its base is twice the width. All right, that's also something they tell me. So the length of its base, so whatever the width is, the base is twice that. Okay, and then there's some height. Material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. Find the cost of materials for the cheapest such container. So where's a good place to start? What about the volume?
X times 2x times h.
Yeah, so I see a connection between something they told me and something I don't know a damn thing about. And they're connected. Good. That's always nice when that happens in math. So the volume from the picture is
2x squared h.
2x squared h. And the volume from what they told me has to be is
10 plus 5.
10, right? You with me? So the volume of this has to be 10 cubic meters, but we don't carry units through our equations, thank God. So what can you do here? How many variables do I have involved in this?
2.
And I really just want one.
I said h.
Yeah, so I can solve for h.
By the 2x squared.
Yeah, so I get 5 over x squared. Is that cool? Just to cut to the chase. All right, now what's more? The most important thing is knowing how to proceed. I mean, so sometimes you don't even know how to start the problem. And a lot of times it's because people try to get to the function you're trying to work with too quickly. I can't get to the cost function yet. That is what I want to work with, right? And in a way you could actually, but you need to have some idea here. So it doesn't matter which one you start with. So this is what they told me. It's going to feed into the formula that I want to work with. And the formula I want to work with involves cost. So what's the cost, for example, for the base?
$10 per meter squared.
Good, $10 per square meter. And what's the area of the base?
2x squared.
Good, so the base will be 10 times 2x squared. Is that cool? $10 per square meter times its area will be the total amount of money it costs to make that base. Costs more money for the base. I don't know what they got down there, but who cares?
Diamond.
Diamonds.
Yep. After we start mining a diamond.
Yeah.
How come it's 2x squared?
What's the volume? The area of the base?
Oh.
2x squared.
Times x, okay.
What's the area of the sides? Are they all the same area? So these two areas, we'll call it area. Screw it. We'll call it the first area.
We know what the height is, so we can't figure out
So
what the area
side
of the
one.
is, right?
There's two of them, right? There's two side ones. What's the area of these sides?
It should be x times h, right?
Beautiful. X times h times 6.
Because that's the cost for the thing per the side?
Yes, I love it. So I'm talking about total cost. The cost will be $6 per square meter times how many square meters it is. You see what I'm saying?
And then
So
that-
$10 per square meter times the area, how many square meters
Oh,
it is.
okay.
So, and we know something better here about H.
We know H is equal to that.
Good, so 6 times 5,
30.
good
over
job,
X
Jeff.
squared.
30, x over x squared. All right, how are we doing so far? So I'm skipping some steps, making it simpler, but the most important idea is what the hell I'm doing. I'm constructing the parts of my equation that I need to work with. I need the cost equation. So I got the cost of the base, I got the cost of the sides, then what's the cost of the other two sides?
Should be 2x times.
Good, 2xh times 6. So it's going to be twice this dude, right?
So 60.
Okay, so what is my cost function?
Is that what we're trying to figure out? We were trying to figure out what.
So remember, never forget, you always have stuff they told you and stuff they ask you. So they asked me to minimize the cost. So the cost involves areas and this money they told me about. Right?
Oh, I see. Okay, so,
So I'm putting that stuff together.
if we get in the function, we can.
Now I want to get a total cost function. Now if you would have done this first, you would have had a cost function with h's rolling around, and then you would have done this and replaced all the h's with that. We just did it the other way around. It doesn't really matter which one you do first. So the key here is just to latch onto something you think you can do and do it, because then it might lead you into what to do next.
Could you have just chosen to fix or to solve for x instead of h? Like, would it matter? Would it have mattered?
The other sides are in terms of x.
So if there's only one h, so it would vary.
Yeah,
more
so it's a
on
little
the x.
easier to go that way. Yeah.
Okay.
To solve for x, I would have had to take the square roots. It would still work, but that's making it unnecessarily.
Difficult.
Yes. So what do I get here for my total cost function? It'll be.
Base
Why did I do
plus
that?
double the sum of the sides.
Good, so 20x squared plus, for each one of these, it's double it, that's right. So I got two sides, so it'll be twice this, I like it. So it'll be 20x squared plus 60 plus 120, so plus 180 over x. Is that cool?
Yes.
Now again, you can't categorize every problem you look at. So you can't start taking notes and say, oh, if they ask me this kind of question, I can do it just like this. That's not the way it works, necessarily, yeah.
How come you set it up as the 20x squared plus 180 over x? Is it just...
You combine the cost of each side.
Yeah, just all the costs added together is my total cost
Plus twice
to make this
size.
thing, yeah.
Did you already double the base, or is it a box without like a top?
Oh yeah, they told me it's open.
Open box. Okay.
That's why I try to make this one not dotted, because I could see it. My art skills, that's the extent. Yes?
Why did we square? You like Mercury, but like square and just the two.
Oh, doubling.
Oh, I'm sorry, yeah, this is a 2 on this.
Oh,
That's the
okay.
area.
Yeah, because I have two sides. Yeah,
Okay.
two sides, yeah. All right, but only one base, the top is open. Okay, so you're not going to put something in that can jump out, hopefully. And so now the biggest problem, just like it is in algebra normally, is creating the function you want to work with. Once you got it, the derivative should be the easy step. Right? Because now, obviously, I want to minimize the cost. I take the derivative, find the critical numbers, and go from there. So what is the derivative of this?
40x plus or minus maybe.
Good.
180 over x squared.
Because remember, that's an x to the negative 1 power. So the negative 1 comes down. And you want to set that equal to...
0.
Good.
Add the 1 over.
So you stare at that for a while.
4x cubed.
You add the 180, multiply the x squared up, divide by the 40, so you get x cubed equals 180 over 40.
Yeah. Why is it x squared?
The x squared.
Oh, here? So this is a derivative.
Oh, yeah.
Yeah. 180 over 40 is 18 over 4 is 9 over 2. And then just take a cube root and you're done. Just like any good problem, the answer is not a pretty answer, right?
Did you add the 180 over x squared to the other side and then multiply x?
Yep. And then
divide by
multiply
40?
x squared and then divide it by 40. Yep.
Okay.
Good. I know you guys can do all the steps. So x will be the cube root Understanding there's two complex answers, but who cares? I can't make a box with complex sides. That would be neat. I want to see that. And what do they actually ask for? You always want to go back. Where was this problem? Number 16. Find the cost of materials for the cheapest such container. So what do I have right now?
X.
X. So how do I find the cost? Yeah, I have a cost function. So you just got to plug that in here. So then you can figure out what that cost is. Now you do realize you could graph this on your calculator and then use the minimum function to double check your work. But I want you to realize sometimes students don't understand why we go through all this stuff if you can just do it on the calculator, but I don't like stuff hidden in the little, in this case, yellow box, right? I want to know what the hell, what kind of stuff is it looking at. It's not really doing this, obviously. It's got some other algorithms. In fact, today's stuff we're going to talk about, some calculators are based on the algorithm we're going to do by hand. It's neat. Anyway. Yes, sir?
Where exactly did minus come from?
Remember this is actually 180x to the negative.
Oh.
So the negative one comes down, yeah, cool. So some of you guys, I think, have gotten it to the point where you see that over x, you automatically know it's going to be negative on the next step. Or you rewrite it first thing before you do any derivatives, just to make it more explicit. Okay, cool. All right, I think it's enough for right now. I can't really do too much more until you guys have some specific questions. So we're going to get into section 4.8. And the idea of Newton's method is, I was talking to somebody earlier about this, and it's really kind of neat how simple the idea is. And now, unfortunately, in statistics, very often the ideas are really difficult, and then the work is easy. In this case, the idea is really simple, and then the work looks disgusting at least. So we're going to try to automate it on our calculators, and I'll show you how to do that. So Newton's method is, if I have some kind of function, maybe I should actually have a place where this happens. There you go. I'm trying to find the root. All right, and again, you could say, well, just put it in a calculator, it's got a 0. No, screw that. We're starting to get to the point where I want to know how does this calculator actually do this kind of thing. So if I want to find the root, I can take first guess. So here's the actual root. I can take a guess and say, okay, I think it's this guy. So, and unfortunately, I've done something where Newton's method's going to freak out. But it's too bad for me. Let me make this a little better. There's so many ways to make Newton's method freak out. And that, of course, is something you give up for because it's so simple. All right, I think this might be better. Well, that was a big change, Jeff. Well, okay. So there's my root. If I take my first guess to be there, the value is right there. The output for x1 is there. It's going to have some tangent line. And, of course, it's horrible. Too bad for me. And it's going to meet the function somewhere else. And that's going to be my second guess. So if I look at the tangent line, there's a much better picture on page 339. Maybe if I make this a little more extreme, I can make it easier to see. Just do what they got here. Yeah, I'll just do the same thing. Okay. So there's my root. If I take a guess to be here, I can find the tangent line at that point. And that's where its root is. That would be my next guess, x2. And see how I got closer to the actual root. Now, of course, there are certain functions that this would die on. For example, if you had a function where it had a horizontal tangent line, if that was accidentally your guess, then the tangent line would take you to infinity, and you would die. That's too bad, right? Or even something less drastic than that, it just takes you so far away that you can't work your way back, right? So there are problems, and that's why your graphing calculator, when you want to find a root, it asks you to give boundaries first. It says what's the lowest, what's the highest, and then your guess. Your guess would be x1, and then it starts doing its algorithm. You with me? In the boundaries, if it ever does something and it goes outside the boundaries, it tries to refine its guess and tries to do it again. Okay, maybe. So, what do you think you do once you got x2? You get its tangent line, because its root would be even closer. So, a lot like, it's not exactly like that, but I can continue this process forever. But I can stop when I'm close enough. And the really cool thing is, how do I tell I'm close enough? We'll see. We'll start to see in all the iterations, x1, x2, x3, x4, x5, I start to see more and more of the digits remaining the same. So then I'm like, okay, then I'm confident out to here that it's right. And the only thing that's changing is the very outside one, the very last digits are changing. So I know I'm at least this close, with this is unknown still. So we'll see it when we do our tables. So let's talk about the math involved. So the idea, hopefully, is pretty straightforward. You take a guess. Your guess has to be somewhat close, especially if your function's really disgusting and does weird things. Right? You want your guess to be close. So we'll talk about how to do that without a calculator. Right? Because I want this to be kind of a purely by hand experience. You'll always be checking the damn thing in calculator. I understand that, but I want to show you how to do this whole thing by hand. Well, how does the math work out here? So this first tangent line. So here's my f of x1. How do I get the equation? Oh, yes, sir.
With Newton's method, would that be able to work on like piecewise functions, or is it only on continuous functions?
So it'll always work if there's a neighborhood around the root that the function is continuous through. If the root exists at a point at the end of one of the piecewise pieces, then Newton's method could very easily fail. Because when you do this tangent line, you can imagine sometimes it would be bouncing around. It would kind of come in from both sides. It'll bounce over here, and then it'll go up and bounce over there, and go up and bounce over there, and come in from both sides. So if your other side, if you have a function and all of a sudden it's there, and doing who knows what, the Newton's method is like, okay, I'll just guess here, and I'll go there, and then holy shit. Right? And it sounds just like that.
So it's kind of based on restrictions for the points that you choose?
So it inherent in Newton's method is nothing about. The method itself is on page 339, and there's no mention of requirements on the function. Now, obviously, it needs to be differentiable, but this is all in some undefined neighborhood of the root. You kind of with me? So as long as there is a neighborhood around the root where nothing freaky is happening, not because of the function's fault, but because of some piecewise definition or something, then Newton's method should work. Right? Okay, so we will talk more about where Newton's method fails after we actually learn how the hell it works. Right? Okay, so what's the slope of this tangent line? Don't overthink it. Yeah, so it's f prime at x1. I like it. So the equation of this tangent line would be y equals. How would you get the equation of this tangent line? Well, you do it like this. We got y minus y1 equals m times x minus x1, right? That's always true for any line anywhere. Well, in two dimensions.
Isn't that kind of confusing considering variables we're using though? Like, are you referring to the?
Oh yeah, I got you. Y minus y.
Y is
Zero.
Okay.
There's no zeros up there, right? Okay. So I got y minus, what's my y piece at this point? F of x1. Equals, my slope of course is
Prime of x1.
f prime of x1. X minus x1, yeah. So now I come back with my x1. You're right. It wasn't because it was x1, it's because it's x1. Okay, so to find this x2, I can plug it into this equation. And what happens, what's y at x2? How do I get my x2? How's that x2 figured out? What happens then? That's where the tangent line is 0. It's the root of the tangent line itself, right? So at x2, y would be 0. I love it. How are we doing so far? Nothing major there.
And the other one? Isn't f of x subscript 1 is 0?
Say again?
Isn't f of x subscript 1 0?
No. So I really want you guys to get this. X1 is a set point, right? A set number. Always. What in here is allowed to vary? F prime is set because it's the slope of that line. It's the same. F of x1 is your y-intercept. It's not your y-intercept, but it's a set point from the point that I'm building this from. You guys with me?
Yeah.
So what is actually allowed? So if I look at this point here, this would be the point x2, 0. And that is a point on this line. So where can I put the x2? In place of the x. And where would I put the 0? In place of the y. So what do I get? I get negative f of x1 equals f prime of x1 times x2 minus x1. So the whole idea here is to start with a decent guess. x1 is decent. It's not right. It's maybe not close, but it's decent. Then I want to figure out what x2 is, which will be a better guess. And then whatever I just did to get x2, I do it again to get x3, and I do it again to get x4, and I do it again to get x5. So the process starts at x1, gives you an x2. Then you get its tangent line, here's x3, and you get its tangent line, and it gives you x4. You go forever. Right? Thankfully not forever.
And this lets you what? Plot the graph if you get the tangent line of everything?
No,
Or
you don't have to. You could, but you don't want to. I'm trying to automate this a bit. I'm trying to take all this individual steps out of this. Yeah.
Does it have to be, you have to use the x-intercept, or can you use any given horizontal line in a decent neighborhood?
I'm sorry. Oh, I see. So, yeah, you can extend the idea from a root. It's not as easy to extend it, but you can extend it to, like, the intersection of this and some arbitrary horizontal line. Is that what you're asking for? Yeah, you could. We're not going to do that here. Okay. But it sounds like a good bonus question now that you brought it up. Yeah, you could do that later. Sort of like Rolle's theorem and then mean value theorem is a more general idea.
So the reason, the reason you got rid of the y there was to get the x2. So for that.
Yeah, now I didn't get rid of the y. I followed the idea. The idea is get that root for the line. So I really want you to understand.
Y is equal to 0.
The tangent line close to where the tangent line intersects. We know from linear approximation it should follow that curve for a while. Eventually it's going to be really far apart here, right? But close to that point it should follow it really well. That's linear approximation. That's section 311 maybe? Yeah.
So then you basically just have 0 minus f of x1 equals f.
So I know if I follow this tangent line to its root that should be a better approximation. Or should at least put me in a position to get a better approximation.
Oh, it's like kind of like proportional kind of thing, no?
I'm not sure how you mean. So
sort of like the distance between that one, just because it's along the tangent line will help you find the distance along this one.
I see what you mean. We are hopefully always getting closer, but we don't always.
Okay.
It depends on what the function is doing. You see how this is very delicate. actually. If the function is moving a little bit, if it just moves a little bit, now when I draw my tangent line, I could be way the hell over there. Does that make sense? Mm-hmm. So it really all depends on how that function, how quickly its slope is changing. So if I go a little bit away, it could be very quickly changing, and when I follow a tangent line, I'm way the hell out there. So it's very, what's the right word? Sensitive. There it is. Very sensitive to minor changes, possibly, unless I have a really well-defined function, which is this is. Of course, we always start there. We always start with the nice ones, and then we say, oh yeah, there's really weird ones later. Well, let's at least finish this out. How do you solve for x2?
Divide by f prime x.
Yeah, divide by f prime, and then add x1. So I get x1 minus f of x1 over f prime of x1 equals x2. And the really funky thing is, the nice thing is, you would think that I would have to then start all over again and go through the whole thing. But thank God that the next step is going to be the same idea. So if x1, if x2 is x1 minus this, gather, then x3 is going to be
X2.
because I've already established the form of x1 to x2. So how do you go from x2 to x3? I've already established the form of how to get there, so there you go. So how do you go from xn to xn plus 1? Get out of there, weird n. Okay. So that's the general form of Newton's method. If you know this, if you take a guess, it gets this whole thing started. The next one is built off of this guess by subtracting this.
And that just tells you like how the tangent line's going like this, basically, or
So each iteration is that next tangent line and where it
along
hits.
the line.
So that would be the root of this next tangent line at x2.
Okay.
And then x4 would be the root of that next tangent line at x3 and where it hits.
So, but like, it's what is it exactly? Is it helping you find basically?
The real root. So my real root is right there, the root where it hits the
root
x-axis
of the
of the function.
Okay.
Good. So that's good to keep in mind. We're always trying to get the real root by taking a rough guess. The tangent line hopefully gets us closer with its root. Then I treat that as my next guess, and then it takes me closer. So there's a lot of operations in mathematics that actually uses that. It says take a guess. Then you do an algorithm to it, and it's a better guess. Then you do the same algorithm to it, and it's a better guess. Right? Keep going until you're close enough within your tolerance. So, as always, a concrete example will help. Right? This is very weird to just sit and stare at, but this is the idea behind it. This is the math that comes out of it. Now let's use the math. And I want to show you how to use a calculator to make this so much easier. Because I know we all know how to subtract and add, and it's amazing. So we're going to let the calculator do all the work. Paid enough money for it. It's time for it to do something. Alright, so first I want to do the math up here, and then I want to show you what it looks like on the calculator and how to go from there. And then I got a nice little handout to help us out a bit. Let me see what I want to take off of here. I'll take this off here. It's disgusting anyway. So let's say we have, I guess we'll do cosine x minus x. And we want to find out where that guy's root is, this function. We want to know where's it equal 0. So Newton's method is really for solving equations. Where if you have if this could be cosine x equals x. You just subtract the x over and then your function is cosine x minus x. You want to see where that equals 0. Right? So Newton's method is actually a way to solve equations by hand. Freaky ass equations. So I want to find where cosine x minus x equals 0. So a real rough sketch of cosine x. Where does it start? At 0, what is it?
It's 0.
So
It's 1.
1. All right. And then it gets to 0 where? Good.
Pi over
2. So it's 0. Now, what is x doing? The function x, of course.
Increasing by pi over 2.
So at 0, it's at 0. At pi, it would be at pi. It should be up here somewhere. So somewhere in here, it's going to cross. Now, see how horrible that picture is? It's not horrible. It's just not specific. Who cares? I just need some rough, decent first guess. That's all I need. So that's exactly what I want to see from you on a quiz or a test. And of course, I'm going to let you use graphic calculators, and you can do that, blah, blah, blah. But it'd be awesome just to see something that's so obviously not from your graphic calculator. You have a rough idea. Get a rough idea. I love it. It's beautiful. It's all you need. Yeah.
How come you drew that straight line? Going
That's the...
Oh,
Yeah, I'm looking at cosine x, and then I'm looking at x.
right.
Because where is this going to equal 0 is where these two things are equal. Is that cool?
Yeah.
So if I look at where cosine x is, and I look at what x is doing, I want to see where they meet. And I do not have to be very precise. I just want to get a good guess, because this Newton's method is supposed to take my guess, make it better. So then if I feed that back into the old Newton machine, it's going to take that and make it better. Feed that back in. So it's like the reverse of a Xerox. Of a copy. Do one copy, then feed it back in, it's even worse. Then feed it back in, it's like a game of telephone, right? Then you final copy, you can't read shit, and then you turn that one in. Alright. So how do I get this thing started? So what looks like it's a decent guess? It's going to be somewhere between 0 and that's roughly
So like
1.5, right? Let's say pi is approximately 3 for being all rough, right? So between 1 and 1.5, I mean from 0 to 1.5, 1 sounds good. How we doing? And again, as long as it's decent, and cosine and x are both well-behaved functions, so I don't have to be terribly close. Yes, sir?
Will it mess you up if you pick a number that's under what it actually is?
How do you mean? Not really. It should be, again, it always depends on the function, but it shouldn't matter if it's below the root or above the root.
Okay.
It shouldn't matter.
Because you're just trying to work your way to the root.
Yeah, in fact, on that example I had here, if I had picked this point, it would have still gotten me,
Okay.
yeah. In fact, it would have gotten to the other side of the root that's in. So it could bounce between and just kind of slowly come in from both sides. It could do
But
that.
it's not exclusive to that type of function. Like, even if it's not so nice, it'll work out that way.
Yes. Depending on your initial guess. So in one way, it's almost like the reverse of chaos theory in a way, because if you pick certain points, they will never get anywhere. But then you move that a little bit. I guess it is exactly chaos theory. You move that a little bit, and then it's fine.
Yeah.
You kind of with me? So there are certain points that will always just take you away, depending on what the function is. Let's get back to concrete. Sorry. So a good first guess is 1. So we're going to say x1 is 1. Let's try one of these by hand, and then I'm going to try to automate this. So what would x2 equal? From the function, from the process, it would be 1 minus f of 1 over f prime of 1. You with me? So the only thing I'm missing really here is, what's f prime of 1? What's f prime of x?
It should be negative sine.
Negative sine x.
Good. Negative sine x.
Minus 1.
Minus 1. I like it. So once you get past the concept really shouldn't be that evil, right? It might just be my bad drawing, but the concept's not too difficult. The work isn't horrible, right? As long as you remember the function, and yes, I will require you to remember this algorithm. I'm not going to have you let you write it on a formula sheet. You must know this. Oh, I'm evil. And if you forgot it, just come up and ask me. I'll tease you for a while, and then I'll tell you. So what's x2 going to be? It's 1 minus, what's f of 1?
0 minus. So negative 1.
Yeah, so it's, well, what's cosine of 1? You got to be careful. You're thinking backwards.
We should be doing this in radians, right?
Yes, I love it. It's got to be radians.
Okay.
I like
It's
it.
going to be like 25, 4.
So it's cosine of 1 minus 1, right? So let me just put it up there like that, and then we're going to put it in the calculator at the end. So 1 minus cosine 1 minus 1, and then what's f prime of 1?
Negative sine.
Negative sine 1 minus 1. and then whatever the hell that is. So let's see. Let's try this. 0.2496. Let's see. So 1 minus cosine 1. Let me make sure that. Good. Where'd it go? Minus 1 divided by. The worst thing about putting in functions like this in the calculator is to be careful about parentheses. Right? So you got to tell the calculator what the top is. You got to tell the calculator what the bottom is. So negative sine 1 minus 1. Cool. Yeah. So I don't know. I get 0.75. Is anybody else trying this?
Are you in radians or degrees?
Radians.
Why not put it as y?
We actually don't do that. I'll show you something even better. Well, that would be fine, but there's no way to make the table feed previous results into itself. That's what you need, right? The recursive idea.
Yeah, I didn't have the 1 minus. That's why
I got the same.
Oh, okay, that makes sense.
It will work as long as you copy that.
0.75 over there.
Yeah.
So, can you imagine this? Immediately, you hope to God there's a way to automate this, because I don't want to work with that damn thing. Right? In fact, most of you guys should know about the temporary memory button.
Yeah.
So, let's kind of do this. So I got x2 to be 0.75036, blah, blah, blah. And that should be a better guess. And real quick, can somebody do cosine? Well, let's do this together. If I do cosine of that,
Minus that.
you see where I'm going. Minus that. See how close to 0 I get. That's decent, right? It's only off by 0.02, roughly. You with me? Okay. So let's see how to automate this. I'm not going to make you guys do this part by hand. What I want to see is exactly this. Here we go. Let me leave this part in there. Actually, let me make this. Okay. So that's the N. That's the general formalization. So xn plus 1 will equal xn minus, what's f of xn?
X. X.
Right, just plug an xn in. And what's f prime of xn?
Negative sine of xn minus 1.
Minus 1, right? Yeah, be careful. And can we just do this real quick? Is that all right? Yay, thank you. And there's more you could possibly, but screw it. I just leave it like that, because I'm going to let the calculator worry about actually calculating things. I don't have to really simplify this too much. But I just need a starting point. Yes, sir?
No, it's plus 1.
She distributed.
He distributed the
Oh, yeah,
one out
so-
and then it canceled out the
It's minus and then 2 negatives here, right? So I just brought a negative up and made that a plus. Is that cool? Okay. So anywhere you see an xn in the calculator, I would put ans. But what gets me started? What does ans mean? What does that little ans button?
Means answer.
previous answers.
Yeah, it means whatever was on the screen a minute ago.
Yeah.
Not ans, yeah.
No, it's answers.
So what you do is you feed in, you just type into the calculator. If you want to borrow a calculator up here, you just type in, our first guess was 1. So 1. Yay, the calculator says 1.
1 equals.
Then you start typing in this whole algorithm. You say, okay, now, so the next one is going to equal that plus cosine of that. So anywhere I see xn, I'm going to put answer, because that represents the last thing that was on the screen. Sweet. Some of you see where I'm going. Minus that. So that's the top. How are we doing? We're just putting ans answer wherever I see xn. Divided by, did I do this right? Yes. Sine
And that's just going to get us, this is ideally just going to get us closer than 0.02 or whatever, like it's going to just bring us even closer than that.
If I do this many times, each guess should be better. So when I feed it into Newton's method, most of the time will make your first guess better.
At some point, like, is there actually a possibility for you to hit 0, or is it kind of like a lot of times you'd have to do that?
It depends on the function itself.
Okay.
Right? If the function is like really flat, then every time you do this, it's going to be taking you far away. Does that make sense? So then it might take, not far away, but you're going to get closer very slowly. Right? And if you're into computer programming at all, you're always talking about, like, searches. You always talk about the speed of a search. Is it on the order of n or n squared? Anybody do any computer programming? So you talk about, like, binary search, and you talk about bubble search, and whatever the hell.
So many things you can do.
Yeah, so how many times it's got to go through to do something, and you try to improve that speed. So there's a whole range of stuff about improving speed. Let's try this. Here we go. Oh.
Are you just using 1 for the answer? Not
Yeah,
the
so,
negative?
exactly. 1. Here we go. There's 0.75, right? Now, its answer. It's in the ANS. It's in that memory spot. So if I just hit enter again, the calculator recalculates the last thing I typed in. It's going to plug that in. That's exactly what this method wants me to do. Keep plugging the last thing in. Keep plugging the last thing in. I love the look on your faces. Some of you guys are like, no idea. But when you do this once, what would I next do this by hand? I would plug this value back in here. And I would do it by hand again. Oh my God, and how far do you want to carry this out? And if you round it too much, you're actually going further away from what it's supposed to be. Oh shit. So if I just hit enter again, so this is x2. That's x3.
You just recall.
It's enter. x4.
Got some numbers staying there.
x5. Now, yeah, exactly. So from the beginning, the 7 was there. So then on the next iteration, when I saw the 7 still there, I was sure about the 7. Then the 3 is there again, and the 9 is there again. So then I'm pretty sure about 7, 3, 9. Then the 0 is there again, and the 8, and the 5, and the 1, and the 3, and everything just about just good.
The 2 is not there. It goes 9, 4, 2. It goes 9, 4, 2.
9, 4, 2.
So the very last digit that you could see.
Yeah, the 2 is the only change there, right? You guys got, so if they would have said, get correct out for the first 4 decimal places, you could have stopped, well actually you'd have to stop here. This is the first time 0 repeated. Right? Yes, sir.
Would you type it in the calculator? Plugging in different numbers.
Okay, so make sure you've got, so you have to first put 1 in. You did that, right?
Yeah.
First put 1 in.
Is 1 just your guess, though? Will that change?
Exactly. Whatever your first guess is, you type that in the calculator, enter. That gets the answer set correctly first. Then you have to input this, but wherever you see xn, you're just going to put
1.
ANS, not 1.
Answer.
Put answer. Because they'll be the last thing plus cosine of the last thing minus the last thing over sine of the last thing plus 1. So every time you enter, it's got a new last thing. Okay. So let's do this graphically. So the answer looks to be 0.739085133 at least. Not 100% sure about that one yet. But if we do plug this in here, and we graph it. Woohoo! And then I do 0. Left bound, enter. Right bound, enter. My guess is right on top of it. 0.7390853. But see, the calculator is smart. It says, I know the algorithm I'm using, and I think they use some kind of modified Newton's method in the calculator. But it wants to give itself boundaries. So if any of the slopes take it outside of those boundaries, it redoes it, or it gives you an error message. Sometimes you get an error message like no sign change or something when you do one of these algorithms. And it's saying, I don't know, you have to improve your guess or shorten your interval. How we doing? How we doing? Again, never poker. You, me, never. Okay. All right, because I don't have enough money to. I don't have any money to lose. All right. So let me give you guys this. Let me let you stare at this, and then I'll let you try a couple on your own. And then we'll look at section 5.
It's like a spoiler, man. It's like this running up. Thank you. Thank you.
Sure. So I'll tell you what, let's do this real quick, just to make sure everybody's got their calculator working correctly. Try to reproduce my results on the second problem.
ln x equals sin x.
Yes. Try to reproduce my results on that ln x equals sin x problem. And if you're having trouble getting those numbers, call me over so then I can take care of individually everybody's got weird troubles. And I forgot to turn this around. That's too bad.